Good morning, Professor, and good morning, my dear friends. We, the Team 2 Physics of Mathematics Department of Sacred Heart College, Devara, are here to present before you some of the thoughts on one of the most interesting objects in the universe, about black holes. I'm Agnes Tom, and on behalf of my teammates, I welcome you all to our seminar presentation. This presentation is divided into 6 small portions, out of which LeyaReginald will be dealing with the questions: what are black holes and why is it called black holes? MeghnaBabu will talk with you about the history of black holes. AshikAugustine will be dealing with the question how a black hole is formed. Anju Sunil will tell you about the different evolution of stars and formation of black holes. Shaheen Muhammad PV will be dealing with the topics general relativistical aspects and also the mechanical aspects of black holes. And at last, myself Agnes Tom will deal with you the mass limit connected to black holes. So, with the permission of Dr. Pius Augustine and all of my classmates, let us start our seminar.
Black holes are among the most fascinating objects in our universe and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light, the fastest known entity in our universe, can escape. It is theoretically defined as an area of space-time with a gravitational field so intense that its escape velocity is equal to or exceeds the speed of light. Black hole can be of any size. It has been found ranging from just a few times our sun, that is stellar mass black holes, up to 50 billion solar mass, that is supermassive black holes. The term black hole was first coined by John A. Wheeler, but its existence was detected hundreds of years before that by many scientists. Many of us assume that a black hole is an actual hole, but it's an object which is extremely dense. The term hole was used because whatever falls into a black hole is trapped forever. It absorbs all the light that hits it, just like a perfect black body in thermodynamics.
Dear friends, today we deal with the topic history of black holes. People tries to solve the mystery behind from the period of Isaac Newton, but the most innovative theory by Albert Einstein, which helps for more findings about the mysterious thing. Later we called it as black holes. Albert Einstein, the creative genius, had completed 10 long years of dedicated work, successfully expanding his special theory of relativity to include gravitation forces along with electricity and magnetism. His general theory of relativity is still considered one of the most beautiful and elegant scientific theories of all time. The pinnacle of this magnum opus was published November 15, 1915 with a concise title The Field Equations of Gravitation. In 1916, Carl Schwarzschild, who is Einstein's colleague and the director of Astrophysical Observatory in Potsdam and an accomplished theorist and mathematician, who wrote back within a matter of days describing the known solution to Einstein field equations. Later, tragically less than a year, Schwarzschild succumbed to a skin disease contracted on the front, joining the millions of WWI fatalities due to disease. He left behind a solution that completely describes how space-time is trapped outside a spherical object like a planet or star. One of the features of this mathematical solution is that for very compact high density stars, it becomes much harder to escape the gravitational field at star. In 1931, Subramanian Chandrasekhar calculates using special relativity that a non-relating body of electron degenerate matter above a certain limiting mass. Eventually, there comes a point where every particle in light becomes gravitationally trapped. This event of no escape is called the event horizon. For this reason, early physics studying these bizarre objects often called them frozen stars. Today, we know them by the names first used by Wheeler in 1967, black holes. Even though the event horizon played an integral part in Schwarzschild's solution, it took many years before black holes were accepted as anything other than mathematical curiosities. In 1972, identification of Cygnus X1 from dynamic observations as the first binary with a stellar black hole. In 1974, Stephen Hawking proves that the area of a classical black hole's event horizon cannot decrease. Stephen Hawking applies quantum field theory of black hole space-time and shows that black holes will radiate particles with a body spectrum which can cause black hole evaporation. In 1989, identification of microquasar V4O4 Cygni as a binary black hole candidate. Moving to the 21st century, we can see that in 2002, astronomers at the Max Planck Institute for Extraterrestrial Physics present evidence for the hypothesis that Sagittarius A is a supermassive black hole at the center of the Milky Way galaxy. Also, in 2002, NASA's Chandra X-ray Observatory identifies double galactic black hole system in merging galaxies NGC 6240. In 2004, further observations by a team from UCLA present even stronger evidence supporting Sagittarius A as a black hole. In 2006, the Event Horizon Telescope beginning capturing data. The very big milestone is that in 2012, first visual evidence of black holes. Suvik Azari's team in Johns Hopkins University using the Hubble telescope Pan-STARRS 1 published images of a supermassive black hole 2.7 million light years away swallowing a red giant. In 2015, LIGO scientific collaboration detects the distinctive gravitational waveforms from a binary black hole merging into a final black hole, yielding the basic parameters, for example, distance, mass, and spin of the three spinning black holes involved. In 2019, Event Horizon Telescope collaboration released the first direct photo of a black hole, the supermassive M87 at the core of the Messier 87 galaxy. The Nobel Prize in Physics 2020 was divided, one half awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. The other half jointly to Reinhard Genzel and Andre Geis for the discovery of a supermassive compact object at the center of our galaxy. Still, black hole is considered a mystery. By this, I conclude my topic. Thank you.
My name is AshikAugustine. We will be dealing with the topic how black holes are formed. So, a black hole is formed when a massive star reaches the end of its life and implodes, collapsing on itself. This means that when a star has exhausted the internal thermal fuel in its core at the end of its life, the core collapses inward upon itself and the star's outer layer are blown away, as you can see in the figure given below. So, as we all know that these internal fuels which are drained after a long time gets inward upon itself onto the core. So these core cannot uh, sustain this much energy. So after a long period of time, they will break out, becoming a big explosion, and the core is blown up away in all the directions. So that's how a black hole is formed. Black holes takes up zero space, but does not have mass. The mass that it had was that of a star. Black holes get bigger as they consume matter near them. The bigger they are, the larger a zone of no return. This point of no return is called the event horizon. As we all know, these points where the black holes can even consume matter coming near them, which have no way of getting back to their original position, or even they can't escape from the black hole. That's what the place called event horizon is. Longer the universe's current age for black holes that started as dead stars to grow to galaxy center-sized black holes. There is a very little evidence of so-called intermediate mass black holes, the ones in between star-sized and galaxy-sized. Both tiny and enormous black holes do exist. As we all know, black holes are formed by a death of a massive star.
Hi everyone, my name is Anju and I will be dealing with the topic formation of black hole. A black hole is a cosmic body of extremely intense gravity from which nothing, even light, can escape. A black hole can be formed by the death of a massive star. When such a star has exhausted the internal thermonuclear fuels in its core at the end of its life, the core becomes unstable and gravitationally collapses inward upon itself, and the star's outer layers are blown away. The crushing weight of constant matter falling in from all sides compresses the dying star to a point of zero volume and infinity. The largest black holes are called supermassive. These black holes have masses greater than 1 million suns combined and would it fit inside a ball with a diameter about the size of the solar system. Scientific evidence suggests that every large galaxy contains a supermassive black hole at its center. The supermassive black hole at the center of the Milky Way galaxy is called Sagittarius A. It has a mass equal to about 4 million suns and would fit inside a ball with a diameter about the size of the sun. That's all about my topic, and the rest will be handled by Shaheen. Thank you.
I am Shaheen Mohammed. I am dealing with the topic general relativistic and quantum mechanical aspects of black hole. When we consider the topic general relativistic and quantum mechanical aspects of black hole, I have to give a brief introduction about what general relativity is. Actually, it is the modern theory of gravity proposed by Albert Einstein. We know to understand the describe and motion of bodies and forces acting in Earth, we use classical mechanics. But when we are considering the mechanics in space and motion and phenomena of the planets, like gravitational redshift and time dilation, Newton's theories become limited. Here, Einstein's theory of relativity. According to this, gravitation is the curvature made by masses in space-time. Space-time means combination of the space and time, and use of it as a coordinate system. Here, the geometry used is Riemann geometry. When we place a metallic ball inside a rubber sheet, it will create an influence in it. If we increase the density of that ball, influence made is also increases. Likewise, heavy bodies will create an influence in space-time. That influence is called gravity. We know black hole is formed by the contraction of stars into a singular point. So it must have infinite density. So it will create a hole in space-time curvature. It should be highly gravitational field. That fields are called black holes. Even horizon. Boundaries of the black hole is called event horizon. From it, even light cannot escape. Actually, the concept black hole was first proposed by Pierre-Simon Laplace. He thought about a star having escape velocity equal to the velocity of the light c. Then he calculated its mass using Newtonian mechanics, and he found out that it will have greater mass than the mass of sun. Gravitational lensing. A heavy light source passing near the black hole will be bent by it. It's called gravitational lensing. Inside the black hole, space-time will be divergent. So we study black hole using quantum mechanics and general relativity. Now this branch is called quantum gravity. According to quantum gravity, likewise Planck's theory of radiation, even the gravitational field is quantized, called gravitons. One of the main paradoxes existing in quantum gravity is information lost inside the black hole? These have many opinions using many theories of physics. According to Copenhagen approach in quantum mechanics, information about a system will be stored in its wave function until that wave function collapses. According to Hawking's theory of radiation, a black hole will radiate slowly. So a material with pure quantum state entering inside it will undergo transformation into mixed quantum state. So information is destroyed. Now we are studying black hole using string theory. One of the amazing facts about black holes in general relativity of Albert Einstein is time will be stuck inside the black hole. So if a man of 13 years old can survive inside the black hole, actually never a person cannot survive inside the black hole because there will be cosmic radiations and strong gravitational field. But if a man of 13-year-old can survive inside the black hole, he will remain as 13 years old forever. Whenever we are going to study what is inside the black hole, it is creating more and more paradoxes. So the studies are still going on. The next part of this presentation will be deal with the magneton.
I'm Agnes Tom, and the topic of the presentation which I am dealing with is the mass limit connected to black holes and also the Chandrasekhar's limit. I think that there is a reassuring quality of everything we know about black holes. The physics of black holes are not normal by any stretch of the imagination. Determining the actual mass of a black hole requires a little bit of mental gymnastics. It is not exactly easy to run measurements on them. That is because any measure won't come back out for all intents and purposes. Things can only enter into a black hole. Nothing escapes. That is why we refer black holes as the point of no return. But we have still been able to infer and deduce many of their properties. We have even determined what they are actually like. I believe that the combined body of human knowledge on black holes represent yet another manifestation of our amazing ability to unlock the puzzles of reality. Now, what is this black hole made of? Yeah, it is made of mass. But the problem is the mass had been collapsed by gravity to a particular point. We have got black holes of different sizes. We have got a regular stellar mass black hole, and then we have the supermassive black hole. But the stellar mass black holes are better understood. It is about 10 to 20 times the mass of the Sun. Now, supermassive black holes are classically defined as black holes with a mass above 0.1 million to 1 million solar masses. Some astronomers have begun labeling black holes of at least 10 billion solar masses as ultramassive black holes. Most of these are associated with exceptionally energetic quasars. Even larger ones have been dubbed stupendously large black holes, SLAB, stupendously large black holes. They are with a masses greater than 100 billion solar masses. Although the scientists noted that there is currently no evidence that stupendously large black holes are real. They noted that supermassive black holes almost that size do exist. Some studies have suggested that the maximum mass that a black hole can reach while being luminous accretus is of the order of 50 billion solar masses. So this is all we know about the mass limits of black holes. I can conclude this section without saying about the great Indian scientist and astrophysicist Mr. Subramanian Chandrasekhar and about his discovery, the Chandrasekhar's limit. His discovery has set the foundation to all we have studied about these black holes. As you people know, the currently accepted value of Chandrasekhar's limit is 1.4 solar masses. He determined that any star remnants 1.4 times more massive than our Sun would be too massive to form a stable white dwarf. After the limit, the force of gravity would cause the white dwarf to collapse. NASA explains that this discovery is basic to much of modern astrophysics, since it shows that stars much more massive than the Sun must either explode or form black holes. I hope that India may have many more scientists like him and let them reveal more interesting facts about these black holes. Let those scientists be generated from ourselves. With this wish, I conclude. Thank you so much. Happy learning.